Swayam Prabha. Digital India. Educated India.
Welcome to the class of design practice for intelligent system design, and we are in the concept generation phase of it, and we are studying currently the trees method for design concept generation and bringing innovation in our design. Now, till the last lecture I have covered in the trees, I told you there are 40 principles and I have covered up to 32 principles. The last was the principle of color changes. Okay. Now, from here I will go to a new principle, principle 33, which is the principle of homogeneity. So, principle of homogeneity tells us that make objects interacting with a given object of the same material. Okay. So, of the same material, that is important here, or material with identical properties. I will give you some examples. Make the container out of the same material as the contents to reduce chemical reactions between the two things. Okay. Friction welding, it requires no intermediary material between the two surfaces to be joined. So, you are sort of invoking the concept of homogeneity. Liquid paper for correcting mistakes when writing, temporary plant pots made out of compostable material, human blood transfusions, transplants, use of biocompatible materials. Okay. In surgery, you will always see that today's surgery, the sutures that is used, the thread to join the tissues, that automatically gets dissolved in the body. So, it becomes homogeneous. Make ice cubes out of the same fluid as the drink they are intended to cool. So, you do not get a sort of problem in terms of dilution. Join wooden components using wooden dowel joints, or you make a solid pencil so called out of graphite, so that the entire pencil itself works. These are very small little examples, but they are used everywhere, maybe for some cost minimization, maximization of the functionality. So, that is the principle, and also reduction of the environmental pollution. So, the principle is widely practiced. Principle 34 is also very widely used. It is called discarding and recovering, not just discarding, but discarding and recovering. There are two parts of it. First part is make portions of an object that have fulfilled their functions go away, discard by dissolving, evaporating, or modify these directly during operation. While talking about one of the principles of intermediary substances, I was talking about space shuttle. Now, the example of the space shuttle can be brought here also, because we do here the discarding and the recovery of the thing, particularly in many other cases. For example, the booster strap-ons in a rocket, you would see that in a rocket it is designed in such a way that along with the main rocket there are strap-on boosters like this. So, they are the stage 1 burners. So, once the rocket reaches certain trajectory, these things are actually dropped down. So, they come down, and then you recover it and use it again. So, discarding and recovering save lot of costs. Casting process, the lost works process is another very good example of it. Sacrificial anode for pollution control. Conversely, the case B, restore consumable parts of an object directly in operation, and self sharpening blades can be also thought of as one such example, but other than that, say automatic rifle or streamer dispenses more wear automatically after a breakage. So, there are some such examples where you restore the consumable parts of an object directly in operation and then you utilize it for future purpose. So, this is principle 34, that is the discarding and recovery. I will now go to the next principle, principle 35, which talks about parameter changes. Now, there are many parameters. So, parameter change is a vast principle. For example, change an object's physical state, example to a gas, liquid or solid is one parameter change. Change the concentration or consistency like liquid versus bar or powder detergent, available linings used to gas turbine engine seals. So, change the concentration or consistency. Change the degree of flexibility, use adjustable dampers to reduce the noise of parts falling into a container, or compliant brass seals rather than fixed geometry seals. Change the temperature, raise the temperature above the Curie point to change a ferromagnetic substance to a paramagnetic substance, lower the temperature of medical specimens to preserve them for later analysis. Change of pressure, pressure cooker cooks more quickly without losing the flavor. So, you can use the pressure as another parameter that you can change. Change many other parameters. Now, here we have one important material actually, which later on we will use very heavily. This is called the shape memory alloys. Here also we play with temperature and also many other ways, like for polymers, other ways of changing the parameter. So, what we do here, as I have shown you here, is that these particular material, I will just give one example of parameter change, that they exist in two different phases. Okay. So, they have a low temperature phase, we will call it as martensite phase, and they have a high temperature phase called austenite. Now, one of the things that differentiates between the two is temperature. Again, another thing can also control it, that is called stress. So, there are two parameters that can change the states. Now, in general, the material has a memory in this stage. That means, whatever is the shape at this stage, it can memorize it. So, what happens is that at a low temperature martensite phase, you are suppose deforming a material by temperature, by all other things, by application of force mostly, you are deforming the material, and then increase the temperature. Once it is beyond the transition temperature, the phase change happens and it goes to its memory shape every time to the same shape. So, the change of parameter is very heavily utilized in this type of a smart material, and that is called shape memory alloys, like say nickel, titanium alloy. Okay, like these parameter changes, phase transition, that means from solid to liquid, liquid and to gas, etc., that is also very heavily utilized. That is principle 36. Like use phenomena occurring during phase transition. For example, volume change during phase transition, loss or absorption of heat during phase transition. You can use it as a sensor. Okay, you can take advantage of the volume expansion from water to steam transition. Such a superconductivity can be another way of taking care of phase transition. Then there are phase change hand warmers, that is very much used today. Okay, so phase transition is again another possibility, because every material, when it changes from liquid to gas or solid to liquid, invariably the shape and size of the material changes, the volume changes. So, you can take advantage of it in principle 36. Now, I come to a very common principle it is the principle of thermal expansion. Thermal expansion is widely used. Remember, from our childhood we are hearing about this fish plate kind of things for connecting, right. So, take the advantage of thermal expansion or thermal contractions for a thermal switch, thermocouples, shape memory I already told you, shrink wrapping, metal tie bars used to straighten buckling walls. So, thermal expansion is very heavily utilized for many such cases. And in fact, if thermal expansion is already being used, use multiple materials with different coefficients of thermal expansion, like bimetallic strips, two-way SMA, passive blade tip clearance, or combine materials with positive and negative thermal expansion coefficient to obtain a kind of a resultant zero thermal expansion coefficient. So, this is the principle 37. We then come to principle 38, which is the use of strong oxidants. So far, whatever principles I have discussed, it is for the first time at least some chemical stimulants use of it we are directly mentioning. And because our world is controlled predominantly the biological world through oxygen, it plays a very important role in this planet. So, strong oxidants utilization, you can see there are so many possibilities. Replace common air with oxygen enriched air, that is something which for scuba diving it is used. Use of nitrous oxide injection to provide power boost for high performance engines. Then replace enriched air with pure oxygen, that is cut at a higher temperature using an oxyacetylene torch, or control oxidation reactions more effectively by reacting in pure oxygen. As you also know that some of the space propellants are actually liquid oxygen, which is combined with liquid hydrogen and burned it together. Expose air or oxygen to ionizing radiation, that is also another possibility of strong oxidation. Use ionized oxygen, speed up chemical reactions by ionizing the gas before use. Separate oxygen from a mixed gas by ionizing the oxygen. Replace ozonized oxygen with ozone. Okay, so, ozone is a very important tool to destroy the microorganisms. So, ozones dissolved in water many times used to remove the organic contaminants from ship hulls. So, oxidants have abundant use, and that is the principle 38. Principle 39 is about inert atmosphere. Just like oxygen is required to do some actions, in some cases oxygen is harmful. So, or there are other corrosion creating substances also. So, you need to create an inert atmosphere. So, in this principle, replace a normal environment with an inert one. Okay, like today we talk about MIGTIG welding, it is based on inert atmosphere. Vacuum packaging, food packaging done in CO2 or nitrogen rich atmosphere, CO2 fire extinguisher. So, principle 39 has two parts. One part is replace a normal environment with an inert one, and another is, as I was talking about, add neutral parts or inert additives to an object. Like naval aviation, fuel contains additives to alter the flash point, okay, or add fire retardant elements for the titanium fire, add foam to absorb sound vibrations, example in speakers, and then fluidic dampers. So, add some neutral parts or some inert additives which will not actually react with the system, and that way you try to perform some functions. Okay. In terms of the dampers, for example, a very common way of adding a neutral part in a damper is like, say, suppose we have a damping material which is used for shock absorptions, and often we actually fill it up with some glass particles. This is something that is very heavily utilized for shock absorption. So, these are glass particles, and this is foam. So, during a shock load, these particles come in touch with each other, and that is how they help in terms of the energy dissipation. So, that is principle 39 or inert atmosphere. Now, we come to the last principle of trees, which is the composite materials. Now, composite is a big thing today. Okay? If you think of the journey of human civilization, it is almost ironical that we actually started with some composites. For example, this straw reinforced bricks, okay, is used in Indus civilization. But generally otherwise, our evolution of material is such that we used in the beginning, say copper based materials, civilization, copper based, and then from there we have migrated towards iron based, and then from the iron based civilization we have come towards, of course, the alloys, super alloys, and then the plastic, so called plastic, and the composites. So, today's civilization is having enormous contributions from the composites. Start it from, say, aircraft structures, low weight and high strength are required. So, what is basically a composite is that you actually have, instead of one material, more than a material, in which we will call one material as the matrix. So, let us say this is a matrix, this is the base material, and this is cheap and this is weak, and this material is further reinforced by some very strong material. So, this is reinforcement. So, this is reinforcement that we utilize in a composite. So, while what is the role of the matrix? Matrix actually holds the system together. And what is the role of reinforcement? Reinforcement increases the property of the material. Just I will give you one example. For example, the very common composite is called glass reinforced plastic, GFRP. Okay. So, what does it contain? In the matrix, if you look at it, then GFRP's matrix is epoxy resin. So, it is a type of a resin. Okay. So, this is one, that is the matrix, and then it can have the fibers like the glass fibers. Now, what is the advantage? If you look at the modulus of elasticity E of, let us say, the epoxy resin. So, E resin will be of the order of megapascal, okay, some 50 to 100 megapascal level. And if you look at the E glass fiber, this is of the order of 100 gigapascal level. So, naturally, if you use this glass fiber with the resin, you are going to get something which will not be as high as the glass fiber, but it will not be as low as the resin. You will get a modulus of elasticity E of a GFRP, which will be as good as aluminum alloy, something like 50 gigapascal. So, that is an advantage, because if you compare the weight, the density, then you will see that it will be at least 1/3 kind of lighter in comparison to aluminum alloy. So, that is a huge weight advantage. So, thus we have seen 40 different principles that has been used by people, and that is how we have been able to trace them from different patents. Altshuler started the work that studying all the patents, that what are the principles that people basically utilize to get a new patent. These 40 principles were figured out. And then the most ingenious part is what I am going to show you now, is to create a matrix, that is what is called the trees matrix. On the trees matrix, you will get on your left towards this direction the features that you are trying to improve. And as I told you that among these 39 engineering specifications, there are always contradictions. You try to improve one, there is something, one of the principles that will be actually worsening. So, these worsening features are listed here, and because we have this as a big trees matrix, right, that 39 by 39. So, I cannot show you the entire thing in one. So, that is why I am showing you here that first 10 features and the 20 worsening corresponding to it. That is what in the first slide, and then in the second slide, then these next the 10 versus the 21 to 39 features, and then I will go to feature number 11 to 20, and again here in the right hand side up to 20, and then in the next slide I am giving you from 21 to 39. Okay. So, that is how in 4 slides I have given you everything that has happened so far. This, of course, this trees matrix, in every few years it gets actually added and revised. So, this is kind of updated list for you. That is why I am telling that so far for any new patent that has happened till today, we will be utilizing these trees matrix. We will be able to see it very soon through the examples. So, keep this trees matrix first of all with you. Okay? It is very important. You do not have to by heart anything, but you have to utilize it. So, now let us see that once this entire trees matrix in our hand, how do we really utilize it? Let us try to see that. I will show you first 3 problems which some of our students have utilized earlier, and then we will take up just random any problem. Okay. So, the first problem we gave it as a challenge to our students is that develop a high power mixer grinder, and naturally if you have to develop a new one, you have to see what are the physical contradictions. They figured out one physical contradiction is the speed of motor grinder increases, but heat generation also increases. So, if you try to high power, if you try to increase the speed, the heat will increase, and power of grinder increases, high power, weight of motor coil also increases, because you have to give more Lorentz force. As the wattage of grinder increases, the noise also increases. So, that is also another worsening feature, and to get more power of grinder, large amount of material is required, that is also worsening feature. Now, once they thought of these physical contradictions, they come up with the technical mapping of it, mapping of technical contradictions. So, one of them is speed versus the noise. Now, this is speed of an object which is rotating. Okay. Then another is speed versus temperature. Then the third part is productivity versus weight, and the fourth part is loss of time versus power. The positive denotes improving feature and the negative denotes the worsening feature. Now, they figured out that corresponding to the first case, that is noise versus speed, noise is number 31 and speed is number 9 in that trees matrix table. So, the relevant contradictions are the relevant principles that are given in the table are 2, 21, 24, 35. Okay. Some of them we can, let us say we can check it also. So, let us go to 31 versus 9. So, improving feature is 9. So, I am just going back a little bit, improving feature has to be 9. So, let us bring 9 as the improving feature. So, yes, this is speed, 9 as the improving feature, and the worsening feature was number 31. That was right. So, that is why it was 2, 24, 35, 21. That is what we have seen. Worsening feature is object generated harmful factors like noise and temperature, etc. So, 2, 24, 35, 21, and then if I look at it again, that this actually some of them talks about intermediary, use of intermediary. We have just seen it in this lecture. then change the concentration, parametric change. Okay. So, these are different types of principles. So, from that they have thought of using the noise suppressors to be used inside housing as one of the solution. The speed versus temperature has 228, 30, 36, and one of the principle they figured out is use flexible shells and thin films. So, they have figured out a solution like fan at lower end of motor spindle to cool the motor coil. Then the other contradiction, weight versus productivity, make parts suitable for operation from these things. So, they brought out polycarbonate liquidized jar, okay, instead of stainless steel. And then the power versus loss of time, make parts universal. So, height adjustable jar and steps, speed control, etc. So, with that they have designed a new grinder, high power, which they claim will have a noise suppressor, fan mounted at bottom, polycarbonate jar and height adjustable jar and step speed control. Now, another problem I will tell you that we have given to students is that a universal skater, that is where you can use the shoe as a skater or skater as shoe. So, again they first figured out the physical contradictions, what are the different contradictions that can come, and corresponding technical contradictions, each one of them. So, they figured out these 5 technical contradictions. Once you do it, then you can go to the trees matrix, and they figured out that what are the principles that people have used to mitigate these contradictions, like 33, 15, 28, 18 for stability versus speed. Similarly, for the other cases, they have been able to figure out that what are the different contradiction principles that you can use. Once they do that, then they thought of the idea like dynamics, okay, wheels with reclination feature that may actually give the wheels, whenever you are walking, the wheels are not, used, and whenever you are skating, the wheels come into action. So, deploy the wheels at that time. So, reclination feature. Porous material, another problem was there. So, they figured out the wheel material corresponding to it. Equipotentiality, so front and rear balancing wheels helped them to do that. Parametric changes, so the fulcrum mechanism they used that helps in maintenance free base. So, that is how the solution they had generated. Now, the third problem is design a compact, lightweight, low power consuming projector which can project from a short distance. So, again they figured out the features that are going to desired, like compactness. Okay, what will be the problem? Temperature will be the problem if it is too compact for a projector. High magnification, distance from screen, low power intensity is a problem, lightweight, robust design, compactness can create system complexity. So, these are worsening technical features. Again they figured out the solutions from the trees matrix which you should be able to do, and then corresponding to all these solutions they also figured out that what are the different solution principles they can utilize, like the principle of local quality. The principle of local quality is used in 2 cases, porous material, parameter changes, partial and excessive action and copying. So, like that the solution has been obtained. So, now let us just sort of try ourselves. Okay. These are the 3 solutions I have just shown you in order to just sort of ignite your mind that how people have utilized the concepts. So, let us just take a random case. Okay. Let us say that I want to design something like let us say I want to design a new spec. Okay. So, my objective, let us say my objective is design new lightweight compact, that is also a problem with the specs, right, compact spectacle. Okay. Let us say this is what. So, how many technical contradictions we can figure out of it? Well, of course, weight is one, right. Let us just quickly think of it, that weight, if I try to reduce, that is the improving feature. What is going to sort of worsen with it? Maybe if I make it very lightweight, maybe the strength is going to worsen, right. So, that is something which is very common, that the strength is worsening. So, this is actually worsening. That means it will become weaker if I make it lighter in weight. And also, let us say that I am trying to reduce the weight and I am also trying to reduce the size. So, to make it compact, right. So, if I am trying to make something compact in terms of the size, sometimes the system complexity increases. So, the complexity increases, right. This is worsening. So, two qualities, the weight is improving, weight versus strength and size versus complexity. Let us look into them in our files. So, let us go back and search them out. Okay. So, we are going to search now. So, we said that weight versus strength. Okay. Let us look into it. Somewhere in the beginning we saw that, right. We have to check the weight of stationary objects. Spectacle is a stationary object, and you look at the strength of it. Okay. So, where do we get the strength? So, we start to search for it. We do not see it here. So, because this is from 21 onward. So, let us go forward and see weight of stationary object here, number 2, and you see it here, area, volume, speed, force, stress, okay, strength, number 14. So, between 2 and 14, I can see people have used these 28, 2, 10 and 27, right. So, out of that, some of them we can very quickly figure it out. Okay. 28, 2, 10, 27, keep in mind 27, 28, right. 2, 10 let us forget, 27, 28 we can very quickly go and see how I can do it. Well, 28 is mechanic substitution. Okay. So, that means if I can somehow think of a different way of opening or closing of the spec, I can actually make it stronger. And 27 is cheap short lived objects. So, people have utilized cheap short lived objects, so that you can keep on changing, right. At least there is one object in the spec, you think of it, which is cheap and short lived. Now, of course, there are other principles. I told you 2 and 10. Let us just check that in earlier lectures we have seen those things, right. 10 is preliminary action. You take some preliminary action on the system, like pre-stress it, so that it does not get bent, and 2 was the taking out. So, you have to use the important part of it, that is to to see that spec's way of expanding or contracting. Now, isn't it that the contact lens does the same thing? So, you are taking out the important property, putting it in, already there is a product there. So, that is what is the beauty of trees, that is how you get a new product. Thank you.